Hello everyone, this is our third lesson in this starting module. So today we're looking at how life on Earth caused environmental change, so how life and its development, its change over time, affected its abiotic factors. So if you remember in our last lesson, we talked about how the early atmosphere was full of things like carbon dioxide and ammonia and methane, and all of those things we can't breathe, like modern organisms would struggle with. So how do we get from that really difficult environment to the one that we are familiar with now? So we talked about how early life was what we called archaea, and these are like primitive bacteria. And archaea, there is a variety, a branch of archaea, which developed into something called cyanobacteria. So cyanobacteria is a type of bacteria, archaea, that develop the ability to photosynthesize. And this is really important because it enabled them to access a freely available energy source that was on the planet that nothing else was using at that time. So we're talking about light energy in shallow seas. And they were able to rapidly multiply and occupy these shallow oceans, using up nutrients that was readily available to power themselves. So things like carbon dioxide and water, which are our reactants in photosynthesis, and resulted in producing oxygen as a waste gas and glucose, which is C6H12O6. Okay, and they use the glucose to go and make their own structures and bodies become more and more complex. And this was great, except everything in the ocean, everything around them was actually found oxygen incredibly toxic. So it was like a pollutant. Nothing had evolved the ways of coping with oxygen because oxygen is highly reactive. So until early life had developed ways in which to cope with oxygen, you'd have periodic times when the oceans would be sort of polluted by it. As this developed and changed, we had these structures developing in the early ocean, and these are called stromatolites. So here we see this picture of this a cyanobacteria colony. In like an early ocean, and you can see they're all under the water to be protected from UV radiation that is coming in from the sun. And you see sort of sun rays coming in. You see all the volcanic activity around there producing more CO2 for the oxygen. More CO2 for the atmosphere, and sort of bubbles coming up, and that's the oxygen being produced. And this left actually a fossil record that we can find. So these are fossiled structures like the ones above, and we even find them nowadays in sort of more extreme environments, sort of highly saline lakes and stuff like that. So these are modern day ones. This is in a lagoon in Chile, I think. So you can see that they're actually above the water here, which is because the lake levels dropped away. Normally they'd be underneath the water level, so they're damp. So why is atmospheric oxygen an important thing? Why is oxygen important? So if we look at this then, so 2.7 billion years ago, we had photosynthesis develop. And this means that we are producing oxygen. Now, to start with, all that oxygen in the ocean, because remember, all life was in the ocean as well. So here's our shallow ocean and then our deep ocean. And we have our stromatolites in the shallow oceans producing oxygen, which is toxic to most life at this point in time. And this oxygen actually reacted with iron mainly. So we ended up with iron oxide being produced. And this iron oxide was actually insoluble. So it would fall out of solution and build up layers on the seabed. Once the oxygen concentrations had got too high, it would sort of start killing off a lot of life. And you would have a layer of black rock form. And then once everything had settled down again, and more oxygen was being produced, you'd have another layer of red rock being produced. And we actually see this in the fossil record. We see the iron being built up layer by layer in the fossil, like in rocks. So here's an example of one of these rocks where you have the iron-rich layers with these darker layers in between. So we've got this periodic oxygenation. After about, after millions of years, what we found was that there's evidence that the iron in the oceans had all been reacted with oxygen, and then excess oxygen started to dissolve out of the ocean into the atmosphere. And this started to occur about 2.45 billion years ago. Okay, and then we start to see evidence of this atmospheric oxygen rising 2.45 billion years ago. This is really important because this early oxygen in the atmosphere, when it meets UV radiation high up in the atmosphere, it undergoes a chemical reaction and we produce something called ozone, which is actually O3. So it's 3 oxygen molecules. So we've got an oxygen there, an oxygen there, and an oxygen there, all bound together. And this formed our ozone layer. And this helps protect us from UV. That comes in from the sun. And this means that complex life, more complex life, can colonize the land. So it can move from oceans to land and colonize it. Which is a really important development. The other thing that oxygen gives us the ability to do is have a more efficient metabolic process. So oxygen permits aerobic respiration. And this aerobic respiration uses oxygen, so we have something like glucose plus oxygen, and that gives us CO2 and water, and it gives us loads of more energy per unit of glucose than anaerobic respiration, and this allows for complex, large life to develop. and it allows it to develop much quicker. The ozone layer that we now know and the sort of oxygen levels that we now know of today formed like fully about 540 million years ago. And that's when we see the sort of modern atmosphere being developed.